Hello and welcome to Numeristical. Today we're going to kick off a new series of videos on the fundamentals of gradient boosting. This will be a 4-video series, and this first video today will be focused on decision trees. So decision trees are the sort of fundamental piece behind gradient boosting algorithm. And we're going to explain how they work, but we're also going to give some motivation, some big picture thought about why decision trees are a good idea and really how supervised learning works. We're going to talk about something called the Similarity Principle, which is this idea that if you've got similar predictor values, you expect your target values or the distribution of your target values to also be similar, and how this motivates the use of decision trees and the use of other machine learning algorithms. So I hope you'll find this video useful, even if you already know decision trees. I think you'll get some value out of watching this, so I hope you'll join me for it. In the second, third, and fourth videos, we'll talk about random forests, and then gradient boosting, and then the various hyperparameters. So that will be the progression of this 4-video series. So before I get into the first video, if you could like the video and subscribe to the channel, again, that really helps me out if you can do that. And with that said, let's go into the first video on decision trees. So let's get started. So we're going to start with some motivation about why decision trees are good, why they're useful, why they're better equipped than some other methods you may have learned. And first, to zoom out and give a really big picture view of this, let's think about the basis of supervised learning. And what I would say is that the basis of supervised learning is something that I call the similarity principle. And the similarity principle basically just says that if two x values are similar, remember x is your collection of features, your collection of predictors. So if you've got two x's and they are similar, then we expect their corresponding y values to be similar. So what does it mean to be similar? Well, when you're talking about numerical features, similar just means that their distance is small. The absolute value of their difference, just how close are the two numbers. If their distance is small, then that means that they're similar. Now for categorical predictors, it's less clear what does similar mean, and there have been a few attempts on how to deal with this, and we'll talk about that further on in the course. But the key is that without the similarity principle, you could only learn about the x values that you actually observed in your data set. So for example, if I'm making predictions about people, and age is one of my features, and I'm trying to find out something about, I want to make a prediction now on a new case, and I want to predict about somebody who's 29 years old, and I didn't have any 29-year-olds on my data set. I had some 28-year-olds and some 30-year-olds. The similarity principle says, well, 29 is close to 28 and 29 is close to 30, so we should be able to learn about 29-year-olds by looking at what happened to 28-year-olds and 30-year-olds. If we didn't have this principle, if we didn't believe that this was true, then we could only say anything about 29-year-olds if we saw exact 29-year-olds on our data set. And likewise, as you put together different combinations of features, you're only able to say something about that combination of features if you believe the similarity principle is true, unless you have an exact carbon copy of that set of features in your data set. So this is, to my mind, really the basis of supervised learning, is that similar x's should give out similar y's. So now I'm going to talk a little bit about linear regression versus the decision tree and how it relates to the similarity principle. So in linear regression, the similarity principle gets basically embedded in the linear model. So the linear model says that y equals ax plus b, plus perhaps some error term. And this line is what guarantees the similarity principle. If I put in two x values that are close to one another into this equation, I will get out two y values that are similar. So more generally, the way this is frequently handled mathematically is by using continuous functions. Continuous functions, by definition, mean that if you put in two nearby x values, you'll get out two nearby y values. And linear regression is, perhaps the most common, the most classical method for this. And one of the reasons that a line is very easy to define, there's two parameters that govern it, the slope and the intercept. And so you might ask yourself, okay, lines are good because they're easy to define, they have very few parameters. What's another function that's also easy to define, has few parameters? And there are many options you could think of. You could think of polynomials, you could think of, other parametric forms. But the one I want to talk about here is a step function. And a step function, in some ways it's complementary to a line. A line says everything happens very gradually. And a step function says, no, you stay the same, and then you jump, and then you stay the same. And so a step function also has only 3 parameters, the way I've defined it here. You've got A, which is the value on the left. You've got B, which is the value on the right. And you've got C, which is the X value at which you make the jump. So now, when we fit a linear regression model, we're able to find the best parameters using matrix algebra. So there's a closed form solution. So if you've taken a linear regression course or you've seen it, you have your big data set of X's, you have your big data set of Y's, and you're able to do an exact calculation and say, this is the best set of coefficients. Best meaning that it will give me the minimum mean squared error on my training set. And it extends very easily to multiple variables. So you just get a bigger matrix, then you have to do some inversion of that matrix and so forth, but it's a closed form solution and it works no matter how many variables you have. And it's guaranteed to find the best set of parameters. So you will, when you do a linear regression, you will get the line that best fits your data, guaranteed. Now with a decision tree, it's a bit more complicated and it's not quite as easy and you don't get the same kinds of guarantees. So let's even go before decision tree. Let's think about just that simple step function. How do you fit a simple step function? Well, the way we're going to do it is just by checking every possible split value. So if you've got n data points, there's at most n different values of your predictor X, and you could just check in between each of those adjacent pairs of values and say, okay, if I split between this one and this one, I'd use the mean on the left to represent the points on the left, I'd use the mean on the right to represent the points on the right. That would give me my step function, and I can calculate what the mean squared error of that particular step function would be, and I could just try them all and see which one I get. So if you've just got a single split, a single step function, you can get the best step function. But it's done not in this closed form way, it's done by checking sort of trial and error across the range of values. So for a single split, as we said, this is pretty easy because if you've got n data points, there's at most n different splits that you would have to check, and that's typically a reasonable number of things to check. But now, let's say I wanted to do a step function that had 3 steps. Well, now to find the best one, I'd have to check n squared, order of n squared, different splits, because I'd have to check every different pair of splits. And this then starts taking a lot more time. Now, once I start getting to n squared splits for big data sets, this is going to start to get infeasible. For 3 splits, it would have to be n cubed. That's going to be even more difficult, and so on. So this quickly becomes infeasible to fit step functions with more than one step. So for a decision tree, the way we solve this is we find the best split and then we proceed recursively. In other words, we find the best split and then we take the data on the left and pretend that's our entire data universe, and take the data on the right and pretend that's our entire data universe, and repeat the process on those 2 data sets separately. So for example, if the best split was at x is less than 7, then we'd split the data into 2 subsets, those that are less than 7, those that are greater than or equal to 7, and we'd find a new split within each of those 2 subsets. And this is what's called a greedy algorithm. This is not finding the best solution. because you don't, the split that gave you the single best split may not be the best one if you're going to have multiple steps. So it's not going to find the best solution, but it usually finds something pretty good and pretty reasonable. Now I've been talking so far about just having a single variable, single x. What if we've got multiple predictors, multiple x's? Well, then we're just going to check each variable individually. So if we had, let's say, age and income, and we're trying to predict something about people, we would look at all the ages and try splitting on each of the ages and see which one gave us the best mean squared error based on that. And then we would also try all the different income levels and try splitting on the income level. So let's go into the decision tree algorithm then as it works. How are we going to put together these ideas around step functions to build an actual decision tree? So we're going to start at the root. We've got all our data. And for each of our variable or predictors or features, we're going to check every possible split of every possible variable and see how well we do in terms of mean squared error if we were to split on that variable on that value. So again, for each feature, for each possible split value, we look at the split, we take the mean of the y values on one side of the split, the mean of the y values on the other side of the split, see how we do, see what the mean squared error of that function is, and just try this for every split of every variable, and then we choose the best one. Now, I described mean squared error as the loss function, and that's typically what you would use if it's a classification problem. You might use a different loss function. So regression, you'll typically use mean squared error. Sometimes people might use mean absolute error, some other function. For classification, usually use something called entropy, which is based on information theory, and I won't get into the details of that, but basically it's tied to the log loss. It's tied to how much you reduce your entropy when you condition on that split. There's also something called Gini. Gini is essentially an approximation to entropy, and it's used because entropy has a log, and Gini is just based on polynomials, and so Gini is a little bit quicker to compute. Logs, running logs in a computer take a little bit more computation time, and when you're doing this many times, that can add up to be significant. So sometimes people use Gini instead of entropy. In practice, I don't find it usually makes a big difference. So we check every split of every variable, choose the best split based on our criterion, and now we've got two separate data sets. We're going to repeat this process on each side of the data split. We're going to check every split of every variable for just this data subset and for just this data subset. And then we're going to stop according to some criteria. So we split, we have two different data sets, we find a split here, we find a split here, and we could conceivably keep going, but at some point we have to stop. So how are we going to stop? Well, there's a few different stopping criteria that you will just choose. So one is max depth, which is where you say, I'm only going to, as I build up this tree, I only want this tree to have a certain depth. So if I'm already 4 splits away from the root, I'm not going to go beyond that. I'm going to stop at max depth 4. Another way to decide to stop is to say, if my data set gets small, then I'm going to decide, hey, there's not enough data here to really learn anything useful. I'm just going to stop here. So you could specify a number and say, when I get below 10 data points, I'm not going to split any further. A similar but related criterion is called min samples leaf, which is you don't do splits that result in a small leaf. So this is slightly different from min sample split. So suppose I said I'm not gonna split anything that has less than 10 data points. But I also might say, and I don't want to have a leaf that's smaller than 5 data points. So that would mean if I had a node that had 20 data points, I could split it, but I wouldn't consider a split that made 3 points go one way and 17 points go the other way, because that would result in a small leaf. And there are other strategies. There are more complicated strategies people use to grow decision trees. There are some strategies where you grow the tree out really, really big, kind of beyond what you'll probably want, and then you prune them back. So there are also more complicated strategies that involve a process like that. Now that's how we fit the decision tree. Now to predict with a decision tree, it's pretty simple. I've got a new point, and you start at the root, and if that initial split said, I'm going to split on age less than or equal to 28, then you'd look at your data point and you'd say, if this person is less than 28, I'm going to follow the left path. If they're bigger than 28, I'm going to go to the right path. And then you get to one of the two children nodes, and each of those children nodes has a rule, a threshold, and a feature. And you just continue down this path until you reach a leaf node. When you reach a leaf node, you output typically the mean of the training data points at that node. So when you built this tree originally and you stopped and you decided this was a leaf node, you typically then just store the mean of the data points at that node. Okay, next we're going to go to the notebook and just go through some of these computations for real so that you can get a good sense of how this works. Okay, so we're in the notebook now, and I just wanted to go through in code how you would go about fitting a step function. So again, to reiterate, we talked about how in linear regression, there's matrix algebra that lets you find the best set of parameters. But for a simple step function, it's more of a trial and error process. You just try every possibility and see which is the best one. So I just wanted to show precisely how that works. So I'm going to create some data. And here's simple data with just a single x value and a single y value. So the way this data was created, I have 25 data points. And the sort of true answer is that if x is less than 7, the y value is 2 plus some random noise. And if you're bigger than 7, you're 6. The y value is 6 plus some random noise. And here's what 25 points of this might look like. So you could see you've got this cloud up here. That's when x is bigger than 7. You've got this cloud kind of down here. That's when x is less than 7. And so to find the best split, we're just going to look at all the unique values of x and find for each, we're going to try each of those splits. And to try a split, what we do is we take the mean of the points less than or the mean of the y values for the x values which are less than or equal to the split value, and then separately take the mean of the y values which are for the x's which are greater than that split value. And then that's going to be our proposed step function. And we're going to find the mean squared error of that step function. So we just say get the mean squared error for the points on the left where we use the a value, get the errors for the squared errors for the points on the right where we use this b value, and then put them together. And we'll just run this through and we'll see for each split. So you can see here's every row we have this split, the mean of the left values, the mean of the right values, and the mean squared error on our training data set. And if you go down, you see we get the minimum. The best one we get is right here. So the best split we found was at x equals 6.46. We've had the mean on the left was 2.16, the mean on the right was 6.1 about, and gave us a mean squared error of 0.855. So you see we got pretty close to the true answer. The true answer, so to speak, was that x should be 7, and that the value on the left was 2, and the value on the right was 6. So we got 2.1 and 6.1, so we're pretty close. So then we'll just plot what that looks like. So in this plot, the solid line is the function we found, the step function that we found. And the dotted line was like another candidate split that was suboptimal, just to show you what a different choice might look like. But you see, for this very simple thing, we kind of found essentially the right step function. Now we talked about how with multiple steps, this is difficult because we'd have to try the number of combinations you'd have to check starts getting very big. And that we're going to use a greedy approach. And I just wanted to illustrate here why the greedy approach isn't always going to give you the best thing at the end. So suppose here's another data set. And here you see we have 4 steps. We've got steps at 2, 4, and 6. Those are the sort of cut points. And the 4 values are 3, 2, 4, and 9. And this is an example of where the greedy algorithm might run into trouble. Because suppose we wanted to just do a max depth 2 tree, so we want to have 4 leaves. You could see that the first split it's going to find is here around x equals 6. And so then what's going to happen? It's going to take these points on the right and try to find another split here. And it's going to find something that, you know, is basically just fitting noise because there's not really any difference between the points on the right. And then on the left, it's going to try doing one more split. And, you know, it'll find one of these splits probably. But we really wanted that left side to break up into 3 pieces. So here's just an example of where the greedy approach fails. Because the single best split is to get rid of this, but the best split into 4 pieces does not start with a split at x equals 6. And here I'm just illustrating, again, the same loop where we go through and find the best split value. And you can see we find the best split value over here at around 5.87, so pretty close to 6. Okay, and just to discuss a couple of implementation details that we didn't get to, some things to think about are what would you do with missing values? Now the classical decision tree, they didn't handle missing values. They would say you just need to impute something. More modern interpretations have come up with better ways to handle missing values. Similarly for categorical variables, there are approaches that say you could try every combination of categories, but that starts blowing up very quick as you have lots of different the size, the number of different categories gets big. So again, a couple of implementation details that we're not going to solve right now, but to keep in the back of your head. Next, we're going to talk about random forests and how you go from a decision tree to the random forest. Thanks for watching. I hope you found that useful. Again, if you have a chance, if you could please like the video and subscribe to the channel, that would really help me out. And soon I'll be releasing the second video in this series, which will be about random forests, how we take these decision trees and build random forests from them. So I hope you'll join me for that. Have a great day.